Hello students, imagine pushing someone on a swing. If you stop, the swing gradually slows down because of air resistance. But if you keep pushing at regular intervals, the swing keeps going. That's exactly what we call forced vibrations. By applying an external periodic force, we can maintain the amplitude of vibrations that would otherwise die out due to damping. So, vibrations under the influence of an external periodic force are called forced vibrations. The applied force here is also known as a driving force. In short, forced vibrations are like giving a swing regular energy snacks to keep it moving. Now let's look at the forces at play. In forced vibrations, three forces act together. First, the restoring force, which always pulls the body back to its equilibrium position. Second, the frictional or resistive force, which continuously reduces the amplitude. And third, the external periodic force, which supplies the energy lost in each cycle. These three balance out, making sure that the vibrations continue. Without the external force, damping would eventually silence the vibration, but with it, motion can be sustained. Think of it like a tug-of-war. Restoring force pulls one way, friction pulls the other, and the external driving force keeps the game alive. Here's the interesting twist. Normally, a body vibrates at its own natural frequency. But when we apply an external periodic force, the body gradually loses its independence. It begins to vibrate with the frequency of that external force. This is why forced vibrations don't match the body's natural frequency. Instead, they sync up with the driving frequency. For example, if a loudspeaker plays a tone at 200 Hz near a wooden table, the table vibrates not at its own natural frequency, but at 200 Hz because that's the frequency being supplied by the external source. Now, how big the vibrations get, the amplitude, depends strongly on the frequency of the external force. If the driving frequency is far from the natural frequency, the amplitude remains small. But if the driving frequency gets close to the natural frequency, the amplitude increases significantly. And when the external frequency exactly matches the natural frequency, something dramatic happens. That's resonance, a concept we'll dive into next. For now, just remember, amplitude grows larger as the driving frequency comes closer to the natural frequency, like a child's swing moving higher and higher when pushed at just the right rhythm. Let's take a quick example. Suppose the natural frequency of a body is 100 Hz. If we apply an external force at 95 Hz, the vibrations occur at 95 Hz with small amplitude. But if we apply the force at exactly 100 Hz, the amplitude becomes maximum. This is because the vibrations are now fully in sync with the applied periodic force. That's the beauty of forced vibrations. They adjust their frequency to match the external driver, and amplitude shoots up when frequencies are close. It's like tuning a guitar string with a speaker. The closer the match, the stronger the vibration. Let's wrap it up. Forced vibrations happen when an external periodic force is applied to keep vibrations alive despite damping. Three forces are always in action: restoring force, resistive force, and the external driving force. The body vibrates with the frequency of the applied force, not its own natural frequency. Amplitude depends on how close the driving frequency is to the natural frequency, small when far, large when close, and maximum at resonance. From swings and guitars to speakers and machines, forced vibrations are everywhere, quietly shaping the world around us. Isn't it amazing how physics explains even the rhythm of motion?